Then I will come back to the lecture slide again and continue from there. Okay? That's kind of what we're going to do today. So quickly, in a high level, to summarize, the objective of transaction processing in a database engine is as follows. There are a couple of objectives. We will talk about the first one. That's the one we've been focusing on, which is what happens if you have multiple users concurrently update or access the same piece of data in your database. What do? And this particular challenge is called concurrent access. And the objective is actually extremely simple. The objective is to say that I want to execute simple statements from different users simultaneously as if they were being executed in isolation. Okay? So how do you understand this particular statement? Okay, let's think about an extremely simple scenario. Don't talk about multiple users. Let's talk about just two users. User 1 and user 2. User 1, user 2. They both try to access the same database. Let's say the students table. Okay? And one user does something for some of the student records. The other user, meanwhile, does some other thing for some other student records. Unfortunately, there is a conflict, meaning that the two of them try to update the same student record at some point in time. Okay? Using the discussion we had so far, if you want to do this properly, you will have to use something like a semaphore to guard against this conflict operations against that student record. But we don't want to do that. We don't want to expose this burden to the application developers, meaning user 1, user 2. From their perspectives, I don't want to use something called semaphore. I don't even know what semaphore is. I don't want to bother with that. I just want to write my code and execute it. As if user 2 does not exist, even from the very beginning. As if, from user 1's perspective, I'm the only user in the system. Even though he or she knows that's not the case, however, the underlying database engine provides this abstraction that I can assume that's the case. Then similarly, for user 2's point of view, he or she can assume that he or she is the only user in the system, even though we all know that's not the case. Okay, that's what we mean by as if they are executing their codes in isolation. In isolation basically means that at any point in time, you are like the only one accessing the database. Okay? What we're trying to accomplish is allow multiple users to access the database, but from each user's perspective, they can think about their execution as if it's totally in isolation. Okay? So that means that let me give you a live demo of that user 1, user 2 example I just mentioned. Okay? Using our MySQL database server. So here, I already log in to the database server using this user account, which is my user account, which is, by the way, also a root user for our database server. Okay, so that's user 1, right here. And user 1, once connected, is going to use our database. And if we show tables, this is basically our class-wide database. Now, before I do anything with user 1, I'm going to log in with another user, user 2, simultaneously to the same database. And for this purpose, I'm going to use the class-wide user account that I distributed to you. Okay? Do you remember that username? 5530 user. Is that right? I think. All right. And the password is, I think, what's the password? 5530 at 18. Okay. Seems like my memory is not that bad. Good. All right, so now you have two users. log into the same course database. Let me use also, and I'm going to show tables as well here. Of course, the two going to see identical content. So far, so good. All of you follow this? All right. Now, what I'm going to do is I'm going to start transaction here. And I'm going to start transaction here as well. So now I have two transactions. One by user 1, one by user 2. So far, so good. All of you follow me? Now, what I'm going to do is, initially, let's say both users, let's say these are some admin people for the university. And they try to update the course catalog for the university. Like some courses are being added, some other courses are being deleted, and so on and so forth. That's what they're trying to do. So user 1, first, before I do any update, I want to look at what's already there. Okay? And user 2, simultaneously, almost at the same time, say, okay, I want to do that as well. So not surprisingly, they see identical content of the table. Simultaneous access to the same data, they see, of course, same copy of this. Nothing so surprising so far. Now, what's interesting is next. Okay, user 1 says, okay, there's no database course. That's wrong. I want to insert into course values. And this is a computer science course. Do you follow what's going on? Okay, I'll do that. And user 1, of course, just like when you lock your car, you want to hear the beep. Right? After you make some change, you want to make sure there's some kind of feedback. So user 1 says, okay, I'm going to check that it's actually being inserted, and it did. Do you see what's going on? You follow what's going on? Yes or no? Now, for user 2, though, if I do this, what's going to happen? Someone tell me what will happen? Based on the discussion we said. Remember, as if you were running in isolation. That's a key word I just mentioned. Okay? With that being said, can you guess what's going to happen if I execute this from user 2? Go ahead.
Right. So I would think that getting all the courses would still not list 101 database.
Excellent. That's exactly what's going to happen. I mean, it seems like no change, but I mean, that's because it keeps displaying the same thing over the same space, so it's as if you're. But 101, the database course, is not there. Even though they're accessing the same piece of data. Do you follow this? Okay? So that demonstrates, this simple experiment demonstrates to you the concept of transaction, meaning that I'm doing simultaneous access to the same piece of data, but as if from each user's perspective, they don't have to worry about the fact that there's another user concurrently accessing the same piece of data. They can just march on as if they're running their code in isolation. Of course, this brings up a bunch of other challenges as well. How do you do this coordination and things like that, which I will talk about in detail coming back to the slide. But using this simple example, I want to demonstrate to you at least what, get a sense what that transaction thing is. You follow this? Now, furthermore, you may wonder when eventually this database course should be made available to other users at some point, right? So that happens when you do something called commit. When you commit, that's kind of like, the way you think about this is kind of, it's not the same thing, but kind of like when you book your flight or book a hotel, you go to the last page, they ask you, are you sure you want to do this? You click on that confirmation button. This commit is kind of like that. So you commit. Now commit marks the end of the earlier transaction. So now we are outside that transaction for user 1. So do you follow the discussion? Okay. Now for user 2, if other than commit, there's another way to end your transaction. It's called abort. Abort means you basically do nothing, as if the transaction has never happened. In different databases use this different terminology. Sometimes it's called abort, sometimes it's called rollback. In MySQL, it's called rollback. Okay, fine, you go back. It's the same as abort. Now, user 2 is outside that transaction. Now, if he or she executes this again, because user 1 has committed the transaction, now you can see this record. Now you can see this record. You follow what's going on? Okay. One last comment I want to make. You may wonder, okay, in your phase 2, I never use any transaction. You ask yourself, yet my changes are, whenever I make changes are immediately reflected. Why that's the case? I never commit, I never roll back, what happens? Okay? You may wonder that question. Okay? The question is answered by when I do the following. There is, in most commercial database engines, there is a system-wide configuration parameter called auto-commit. Auto-commit. And by default, the auto-commit is set to up. It's a Boolean value. From the name, you can kind of guess what that means, right? What that basically means is when auto-commit is set to true, every single statement you type is a transaction by itself. You don't have to explicitly type start transaction and commit to indicate that one or multiple statements in between is a transaction. Every single statement by itself is a transaction when auto commit is on. And the effect of that statement is immediately reflected because it's like once you execute that statement, you commit. Do you follow what I'm saying? Okay, if you want to make a multi-statement transaction in auto-commit mode, you have to explicitly type start transaction and commit. That will override the auto-commit effect. Far so good? One last thing before I switch back to the there are, of course, many other parameters control the performance and behavior of your transaction engine. Obviously, I cannot go over all of them. But hopefully, by the time we finish the discussion on transaction, you can understand some, if not all, of these parameters. Now, the last thing I want to show you is something called Shoukry Table. And look at the course. And it's important to note that especially in MySQL, later on, the reason I mentioned this is later on I don't want you guys to be confused. When you start using MySQL and you don't observe the same behavior as I demonstrated here. MySQL as a database engine has different so-called storage engines. Actually, we will talk about storage engine a little bit after the discussion transaction, if time permits. Okay? And different storage engines give you different implementation and different support for transactions. The default storage engine in MySQL is called MyISAM. MyISAM. And that storage engine does not support transactions. Does not support transactions. However, you can easily change the storage engine for any given table, not even just any given database, for any given table inside MySQL. So in this case, I actually changed this course table to a different storage engine called InnoDB. And that InnoDB storage engine does support transactions. So later on in your career, if you want to do some database development using MySQL and you want to support concurrent user access to your data, make sure you are using InnoDB storage engine. Make sure you're using the InnoDB storage rather than the MyISAM storage engine. You follow that? I think some of my tables are in the other storage engine. Let me see whether I can show an example of that. Everything here is same. Okay. See, that's a different storage engine. That's the default storage engine. You may wonder, why bother with different storage engines? Because there's a trade-off. When your storage engine supports transactions, when you decide to use the storage engine that supports transactions, that comes with a lot of overhead. That we will actually talk a little bit about that, how you implement support transactions. That introduces a lot of overhead. If you know your table not going to have concurrent updates, then why sacrifice your performance because of those overheads, if you know that's the case? MyISAM is optimized for query processing. If you know you don't have concurrent updates, then you should use that to give you much better query performance. That's why you have different storage. And in fact, people build companies, business, out of just designing a specialized storage engine for MySQL. If you know this database system that well, you can build a company by just design your own storage engine and plug in that as a service for others to use. If your storage engine provides some appealing feature, then they're willing to pay and use that. Like one company called CockroachDB, I know the founder very well. You guys can Google it. Basically, support, give you some compromise trade-off between transaction processing and query processing. Just to give you an argument. My Facebook, by the way, Facebook is our newest recent data, right? The entire Facebook data is stored in MySQL. Of course, not a single MySQL database. They are using a MySQL cluster database. Everything you access on Facebook is from their MySQL database. Yeah? And that being said, of course, being Facebook, they of course build their specialized storage engine for MySQL. So they use these standard engines as well as some specialized engines they build for MySQL. Okay? All right, so far so good. Everything sounds good to you? Okay, now let's come back and try to understand transaction. Now we have seen the real example, okay? By the way, it's fairly easy to call and initiate transaction from your Java code and PHP code or JSP code, right? It's in the same way as if you were executing SQL statements, right? Typically, the higher level language will also give you some kind of abstraction for transaction. For example, instead of execute statement, you may have prepare transaction and execute transaction, where prepare transaction allows you to supply a list of statements that go into that transaction, and then execute transaction will submit and execute that transaction, okay, in batch. A different database engine and also different front-end code, like JDBC, PHP, will have different kind of abstraction for this. But once you understand the basics behind the scene, it's fairly easy to figure out those APIs. Not that hard. Okay? For good, any questions before I proceed? Yes.
This is where T1 and T2 from the book comes in. The table of
T1 and T2.
Yeah, transaction 1, transaction 2 tables that keep them organized.
What do you mean by? Okay, so are you talking about the example the demonstration I just did?
I believe so, yeah.
Yeah, so we have user 1, user 2. User 1 initiate a transaction. Yes, you can call that T1. And user 2 initiate another transaction called T2.
Okay.
What I demonstrated is, T1, T2 were executing in parallel, but from user 1 and user 2's perspective, T1 is as if being executed in isolation, so does T2.
Okay.
That's the purpose of that demonstration.
All right, thank you very much.
No worries. Now, some basic things. So I went through this already. Okay. So concurrent access is just one aspect of transaction, right? The other aspect of transaction, a really important property of transaction is this resilience to system failures. Resilience to system failures. So the idea is, what if you are in the middle of doing something that's really important, like you're moving some students out of the applied database and moving them into the archive database, and you want to make sure the following: make sure that, okay, I want to do this for all students being affected. Either all of them have been moved over to the archive database, or none of them has been moved over to the archive database. Okay, so this is all or nothing semantics. The worst case you want to avoid is the following, which is you're moving, maybe, let's say there are 10 students being affected. You have moved 3 students over, and the other 7 students are still in the active applied table, and in the middle of that, server failed, lose power or whatever. Then once you recover from that, you as the application developer will face a hard time in figuring out what records have been moved over, what records are left behind. Why? Because system failure is kind of random event. It's hard for you to know exactly the timestamp for the system failure, and also how many records have been moved over at that time, and how many records are still left behind. It's really hard for you to do that. Okay? So you want to have this all or nothing semantics. In other words, you want to be resilient to system failures. Let's say you're doing some barcode to the database. In the middle of that, system has crashed. You don't want to have some data being imported into database while the others are still left behind, and you don't want to be left in a situation where you don't know where the boundary is. You don't want to be left in that situation. Right? To give you a specific example, this is the apply and archive example I was referring to. So the idea is you have data in the apply database, and for those students you decide to reject, you're going to move them to their records to the archive database. So you're moving data from one table to another table. Let's say imagine they're on disk, you're moving them over. In the middle of it, let's say you move some of the records over and system failed. And when you recover, you don't know where that failure has happened and how many records are being affected because of that, if you don't have some kind of semantic guarantee from your system. So we use transaction to guard against such failures. So transaction give you this all or nothing semantics. I'll give you another example. You have a lot of updates buffered in memory. Okay, that's your database. So the important thing to understand is how computer works. You take any computer. Right? Computer works with a hierarchy of storage space. You started with cache in your CPU, then you also have memory, then you have your durable storage, typically with a hard drive or SSD drive, solid state drive, that are durable. Durable means that in the case of you no longer have power, your data will still be there. But that's not the case for data cache in memory or CPU cache. If you lose power, those data are gone. So similarly, in your database system, the changes you're going to make for your data are always made to some copies of the data cached in something called buffer. Buffer is kind of like a reserve space from your memory, reserved to hold data for your database system. Okay? And when system fails, this part will be lost forever. Because that's in your memory. That will be lost forever. This is persistent. But the challenge is you don't know when system gonna fail. And when it does fail, that content, the state of the buffer, is undecided. Meaning you cannot decide the state of the buffer before system fails, because you cannot predict when system gonna fail. You follow me? If the underlying database system doesn't do something about it, and system fails at a random point, then the changes you make will not be made persistent to the database because of this. You follow this? And I want to demonstrate this particular point going back to our database. Okay? Now, what I'm going to do is I'm going to quit this guy. I'm going to become root right here. So now I'm the root. And I'm going to here I'm going to just prepare to restart the database server. Here I'm still under user 1. I will start another transaction. So far so good? Now I'm going to insert another database course. Now if I now I have two database courses. And furthermore, I'm going to delete, let's say I want to delete one of them. Okay? But let's say you type this one. You made a mistake. Course ID, I don't know this. Course number, okay? So you were meant to make it equal, but you end up typing greater than. Too bad. Okay? You left with only database courses. Okay? So that's too bad. But luckily you are in a transaction. If you roll back, these changes will as if never happened. Let me show you. Okay? Like nothing had ever happened. Okay? You follow this? Now, let me try to do the same example again. Start transaction again. Let's say I delete this. Now, you should have only one course left because the insertion, the second time I was doing it, I didn't insert that database. Now, let's say these are the changes you have made, but you haven't committed yet, and system fails. This server restart, I'm simulating like if a server had failed. You follow that? Okay. Let's wait for the server to restart. See whether it's already restarted. So it's not restarting yet. Okay, let me connect to the database again. So I'm going to select from the course. What you notice is after database has restarted, what happened? The changes you were making are gone, as if it never happened. Why? Because you hadn't committed your change at the time of system failure. Do you follow what I'm saying? Yes.
So, out of curiosity, where are those changes being stored before you commit? Is it locally, or?
That's a deep question. I will answer this as we talk a little bit more about transactions.
Just like out of curiosity, like how common is it for something to fail?
If you are running a single server mode, the chance of your server failure is low, actually, pretty low. Now imagine you work for Facebook and Google, where you have tens of thousands of machines. Failure is a constant. Somewhere you're going to have failure all the time. That make sense? It's kind of like, what's the chance of, before I take any flight, I always ask myself, what's the chance of plane crash? Seriously, I ask that question all the time. And they always tell me, it's like 1 out of 10,000. That sounds fairly low, right? But then, if you ask another question, how many planes we have on the sky at the same time? Well, I'm sure we have more than 10,000 planes. So one of them going to jump, if you do the math. That doesn't look any good anymore. That make sense? That's kind of in response to what you were asking. So I got so worried about that, I started watching YouTube. I highly recommend this. I started watching this thing called Air Crash Investigation on YouTube. It's a super fun series to watch. It tells you why plane crash, and also they do investigation of it. Actually, watching that helped make me feel safe about flying, because every accident makes the next flight safer, because they figure out what's wrong and they do something to guard against that. Does that make sense? So I recommended this to one of my friends, and he fell in love with it. Until one day he got into trouble with it, because he was taking a long flight across the ocean, and he got bored. And pulling out his laptop, start watching this. And the lady sitting next to him was having a nice started having conversation with him. Oh, that's a nice, where are you watching? And she started paying attention, and she said, you must be nuts watching this over a flight over the ocean, right? So the point is, failure, if you look at an isolated node or isolated event, the probability of failure is low. But once you look at massive number of nodes or massive number of events, even a small probability can lead to failures all the time. That's the point. Okay. All right. So now let's look at how transactions help you guard against failures and offer this concurrent access semantics. Okay. We're gonna briefly talk about this, but keep in mind this particular course is not about the kernel of the database system, like the question you were asking. So we actually dedicated 2 lectures on that in the grad level database course to just explain that. So in the undergrad version, the main objective really is for you guys to understand what transaction is, what are the semantics it provides, and some basic knowledge about how that was provided by the underlying database, not every single detail on how transactions are implemented inside the database kernel. Okay. With that being said, let's look at this together. Okay. The goal of system failure is you guarantee this all or nothing execution, regardless of failures, like I have demonstrated. Right? If you have made one change or multiple changes, and before you commit, if system fails, you should restore the system to a state as if nothing had happened. Okay? So this is the all or nothing semantics guaranteed by transactions. So solution for both concurrency and failures are something called transactions. So a transaction is essentially a sequence of one or more SQL operations treated as an atomic unit. The keyword is atomic. I explained why people use this keyword atomic unit, because they used to believe atom is non-dividable, which we know that's no longer the case. Physics has made so much progress, people know there are smaller particles than the size of atom. But at one point in human history, people believe that atom is really the smallest part you can go. Molecule is like this big, atom is like really, really tiny. But now the view of physics is atom is like this big. They're thinking smaller than atom as well. But at that time, atom is like the smallest unit. Then whenever you want to have this all or nothing semantics, you refer to that as atomic unit because of that. And transactions appear to run in isolation, and if system fails, each transaction's changes are reflected either entirely if the transaction has committed before system failed, or none of the changes made by that transaction will be reflected. If this happens, if the transaction has not committed yet before system fails.
Say you're committing and in the middle of a commit.
Okay. Very good question. So let me repeat the question. The question was, what happens if you are in the middle of committing and system fails? You follow this? The fundamental reason is, and in fact, commit, and for that reason, does. These are they are not atomic because it takes time to push those changes to the persistent storage and take time to erase those changes you have made, right? So that's a very question. That's a very interesting question. But to answer that, super involved. So I will just assume, for the purpose of this course, we're gonna assume that they are commit and rollback are atomic. So the question you ask will never happen. We assume that's okay. In practice, no, that's not the case. Okay? So transaction begins automatically on first statement and on commit transaction ends, and a new transaction can be started, and the current transaction ends on session termination. What that means is when you quit, for example, you open a JDBC connection, and if you haven't committed your transaction or roll back your transaction at the end of that JDBC session, by default, this will simply roll back itself. Okay? Now, the next slide, I'm going to introduce this famous ACID property. You guys all need to remember this keyword. You know, if you have taken a database course, and after taking the database course, you go and tell others, oh, I know database, and then you don't know this keyword, people will laugh at you. People will laugh at you. Okay? And you say, oh, I know database. Then they say, okay, what about ACID? They're like, what do you mean? You can also play this card the other way. You can bluff as well, right? Like you never taken a database course, or you did take a database course, but you didn't do so well. But you can still bluff. You go around and you say, oh, I know database well, like ACID, that's easy. And people will give you a serious look. Oh, this guy, this dude knows what he's talking about. Even if you know nothing and you bring out this word, ACID, you will gain some respect. Initially, you know, over time, you know, they will figure out, oh, you know only this word, but you know nothing about under the hood. Right? But hopefully by then, you gain some time, you hire somebody to work for you, then you can ask, okay, my time is valuable, he or she can explain this for you. That's what happens in business world. Right? Okay. All right, so ACID, what's ACID? Okay, let's explain this one by one. First of all, I'm gonna explain the letter I. I stands for isolation. Isolation. So we've been talking about isolation for some time right now, right? We've been talking about isolation for some time. What we need to formalize. What do we mean by transactions appear to be running in isolation? What do you mean by running in isolation? We need a formal definition for that. So this has actually different isolation so-called levels. different isolation levels. And different isolation levels give you different semantic guarantees, The strongest isolation level is what we call the serializable isolation level. Or in short, serializability. Okay, serializable isolation level refers to the following. If I have multiple transactions like this, these transactions coming out of different users. By the way, the same user may have more than one transaction. Okay? So when I have, let's say, in this case, I have 5 transactions, that does not necessarily mean I only have 5 users. I may have 2 users. I may have 3 users. I may also have 5 users. Okay? And they all try to execute their transactions at the same time, simultaneously. And each transaction consists of multiple statements. That's kind of the setup, right? Serializability or serializable isolation level, the definition of it is actually really straightforward. It says you can execute transactions simultaneously, and each transaction can be as complex as you want that to be, meaning that it can have 1, 2, or hundreds of SQL statements. I don't care. Can be as complex as you want that to be. And you execute that means in parallel. That's fine as well. You can do that. But at the end of the day, when you finish executing these transactions, the end effect of your database, must be equivalent to one of the serial executions of those transactions. To understand what I said, we need to understand a few things. First of all, we need to understand what do we mean by TX stands for transactions. First of all, we need to understand what do we mean by serial execution of transactions. Well, that's actually fairly easy. Using this example, I have T1, right? A serial execution of this is simply okay, these are my transactions. One of the serial transactions is like this. Meaning I execute everything from T1 all the way to the end. And only after I'm done with that, I start executing T2, and so on and so forth. You follow me? You may wonder, wait a minute, isn't that the only way to execute this anyway? Not necessary. Let me focus on 2 transactions, T1, T2. Let's say T1 says, okay, and T2 says, okay, insert a record into student. Do you follow this? Very, very simple example. To follow this model, you cannot execute this until this is completely done. You may wonder, what's the big deal? I execute this and do this. Let me show you what happens. Okay, back to our database. start transaction. Okay, let me. Okay, the first transaction says select star from course, and the second transaction will all I need to do is supply a student ID. I don't need anything else. Okay. Okay, actually delete is easier. Okay, let me. Let's say I want to delete from student where. Am I in a transaction order? Do you remember I started the transaction here? I did. Okay. All right, cool. So let's say that's what I want to do. Do you follow this? If you were to execute them in serial order, what that means is you have to wait for this to complete before you enter and execute this. Okay, this user cannot even delete because that's the way I set up the database. Okay, let me swap. Here I'm gonna delete. And here I'm gonna select from course. Do you follow this? Seems like no big deal. You execute this first, then you execute this. Done. They've been executed in serial order. Now let me go back. Start transaction again, so that delete as if never happened. Now I'm still in this transaction. Now let me change this to a different table. This table now has about 500,000 records. So if you were to execute them in serial order, what's going to happen? You'll have to wait for this. You cannot do this. You have to wait for that to finish before you can execute this statement from T2. And this will go for a while. 500,000 records. I'll go until the end of this course. You follow what I'm saying? If you were to execute them in serial order, T2 cannot proceed until this is finished. But in reality, that's not the case. You can proceed without any trouble. So obviously, we are not doing this. We are not doing this. The database engine is not doing this. You follow what I'm saying? You need an example? Yeah? You agree? However, in reality, we're not doing this. We are basically executing them in, so this is left function. In reality, we are executing them in parallel. However, the definition of serializability or serializability or serial isolation level is that the end effect, you can execute them in parallel, but the end effect must be as if they've been executed in sequential order. Using that example I just showed you, one is doing a select all from test or course table. The other one is deleting a student record. What will be the end effect? Even if you to execute them in parallel. What's the end effect? The end effect is equivalent to, or it's actually also equivalent to this. In this case, these two are the same. Do you follow that? Yes? You follow me? You may wonder, okay, what's the big deal? So we execute everything parallel. The trick though is, it's not always the case that if you execute things in parallel, you will get any effect equivalent to as if you execute them in some serial order. Let me give you another example. Before I do that, let me make sure I roll back the changes I made. I don't want a student to be deleted. So let's consider this transaction, okay? Two transactions. Transaction 1, transaction 2. Two statements. Transaction 1 has two statements, transaction 2 has one statement. It's similar to the example I demonstrated to you. Instead of using students, one is, in this case, we're using a user table, right? Let's say transaction 1, all you're doing is selecting who are aged between 10 and 30. Extremely simple. And as just as most people, when you lock your car in a parking lot, you want to hear the beep twice. How many of you do that? I do that. Same here. When you say, okay, return me record between 10 and 30, you execute again. Make sure that indeed you get all users aged between 10 and 30. You execute that twice. Before that, that's what transaction 1 is doing. Now, transaction 2, by the way, the way you understand this is there's a y-axis, that's time. The time is this direction. You follow this? In between your two statements, another guy comes in and in parallel execute this statement here. Okay? You follow this? Yes? Now, assuming these three statements happen in the way like they happen here, let me ask you this. Are they equivalent to, is this equivalent to T1 then T2? How many say yes, how many say no? If you say yes or say no, can you explain to me why? What happened here? Is that equivalent to complete T1 then T2, meaning a serial execution of the two transactions? Yes or no? What happens here? Is that equivalent to T1 then T2? To understand this, let's look at what is T1 and T2. T1 and T2 means that you execute those select statements from T1 twice. Then you execute that insert statement. What happens? That select statements will return all users aged between 10 and 30 that were in the database without that new user that was just inserted. I don't know who were in the database, but whoever in the database aged between 10 and 30 will be returned twice. That's the effect of T1 and T2. And T1 will never see that new record being inserted. That's T1 and T2. You follow this? What if you do T2 then T1? What's the effect of that? Can someone tell me? If you do T2 then T1, what happens? Come on, somebody tell me. You guys should be able to do this, right? No? Go ahead.
You'll get all the users that all will be equal. You'll just get two copies.
You get, from T1's perspective, you got everything aged between 10 and 30 twice, plus this new user twice. Because its age is between 10 and 30, satisfying your core condition. So one thing we observe, in this case, these two are not equivalent, at least, in this example. You follow that? Is the given schedule, is the given sequence of execution equivalent to T1 then T2? We just said no, it's not equal. Why is not equivalent to T1 and T2? Because using this sequence of execution, the first time you execute this select statement, you see everything aged between 10 and 30 that were in the database. The second time you execute this statement, what do you get? You get everything aged between 10 and 30, and this new record here. Why? Because it has committed. So the change is reflected. Do you see this? So the two times you execute that select statement, you get slightly different thing. It's kind of like in a parking lot, you log your car. First time you press the button, you hear beep. 2 seconds later, you work a little bit, you press the button again, you hear, yes, you hear something, but you don't hear beep anymore. You hear beep, beep. I don't know about you, I got worried a little bit that something happened to my car. It's not equivalent to this, and it's also not equivalent to T2 and T1. You follow me? So the purpose of this example is to demonstrate to you that when I talk about parallel simultaneous execution of transactions, it may create problems. It may lead to a sequence of events that's not equivalent to a serial execution of these transactions. Okay, that's the purpose of this example. Do you follow this? You don't get a serial execution of your transactions. Now, we understand what's a serial execution of transaction, right? What about one of serial executions of these transactions? Why? Because given, like using two transactions, you already see there are two serial execution of these transactions. T1, then T2, then or T2, then T1. What about n transactions? If I have n transactions, how many serial order I have? Can someone tell me? How many serial order I have for those n transactions? How many serial execution orders I have for those n transactions? Go ahead.
N factorial.
Excellent. Can you explain why?
Yeah, because you can start with one of n, and then for each one of those you have one of n minus 1, and then for each of those routes is n minus 2, and so forth.
Excellent, excellent. So basically what happened is think about these are you kind of tennis balls or ping pong balls, and you want to place them into a sequence. And this sequence has n positions to fill. Position 1, position 2, until position n. The first position, how many choices you have? How many choices you have? You have n, right? Any one of these can go here, so you have n choice. Now coming back to the second position, how many choices you have now? You no longer have n choice because you choose somebody for that position. So you're left with, let's say you choose T2 to go here. Now you're left with what? How many choices you are left with?
N minus 1.
Yeah. And you multiply this together. That's the total number of choices you have, and that's exactly n factorial. Okay. So given n transactions, you have n factorial different execution orders. And furthermore, we already see that the effect of those serial executions are not the same. Using this simple example, I already demonstrated to you that T1 and T1 then T2 is not necessarily the same as T2 then T1. And generalizing that to n transactions, and that's like the simplest transaction you can have. T1 just executes the same selection statement twice, T2 just doing insertion. And you can imagine for real transaction with multiple statements, those transactions you do on Zhaoqiao.com, on Expedia.com, on Amazon.com is way more complicated. The effect, obviously, is not necessary to be the same of these n factorial orders. Do you follow me? Yeah? Okay, now here comes the important claim. The important claim is serializable isolation level says if your database is in serializable isolation level, then you can execute transactions in parallel if and only if the effect of your execution is equivalent to one of the serial execution. That's it. That's the definition of serializable isolation level. What that means is this particular example I show you here, this particular schedule, meaning the way you're interleaving actions from different transactions, this is not allowed in serializable isolation level. This will not be allowed in serializable isolation. Why? I just argue for you. It's not equivalent to this. It's not equivalent to T1 then T2. It's also not equivalent to T2 then T1. That's the only two serial executions when you have two transactions. 2 factorial equal to 2. You only have these two possible orders. And this is not equivalent to any one of it. Henceforth, it cannot be a valid execution in serializable isolation level. Follow me? So if you configure your database in serializable isolation level, this particular schedule will be rejected. This will be rejected. Okay? But as I said, serializable isolation level is the strongest isolation level you can expect from a database engine. Being the strongest isolation level, that also means it reduces the chance for parallel execution. For example, that schedule we just looked at will be rejected. What does that mean, by the way? What's so important about parallel execution? You wonder, okay, being rejected, fine, I don't do this. I wait for T1 to finish, then I do T2. What's wrong with that? Well, I just demonstrated to you what's wrong with that. Right? If one transaction takes a long time, the other transaction has to wait. Imagine if that's the Amazon.com business model. You go there, you wait for other users to finish before you can place the order. Nobody's going to use Amazon.com. Maybe you will, I will not. My time is valuable. My time can be better spent on waiting. I hate waiting. Now, whenever I go to DMV, I got mad. But this morning I went to DMV. It's not too bad. Like, I didn't wait. You follow that? So, how do you address this? How do you address this problem? Well, you have to compromise, right? It's just like in life, right? You cannot get everything. I hope I can get everything, but you cannot. So you have to compromise. The compromisation we come up with is relax the isolation requirement. Do not require serializable isolation level all the time. Do not require serializability all the time. Henceforth, people define other isolation levels. In particular, there are 4 really popular isolation levels used by commercial database engines. We talk about the strictest one. The strongest isolation level is serializable. Serializable. Okay? Now, before I talk about these 4, I will talk about the weakest. The strongest is serializable, right? We just saying. What's the weakest? Can someone guess? What's the weakest?
Would it be parallel?
Huh?
Would it be parallel?
Say again?
Parallel?
What do you mean by parallel? Give me a definition. Parallel, that's vague, right? That's undefined. What do you mean by parallel?
Maybe just any order of interleaving would be allowed?
Excellent. Any order of interleaving actions will be allowed from any transaction. That's the weakest transaction. But that's kind of like, it's Wild West. It's like moving back 200 years being in Salt Lake. Not even in Salt Lake, in southern Utah. Good luck, you're on your own. Like you are the application developer. Database doesn't give you anything. Database only serves as a storage engine. You have to do all the careful control in your application logic. Do you follow that? Excellent. Okay? Excellent point. You can interleave action from different transactions in any order without worrying about messing up the semantics at all. That's the weakest isolation level. There are 2 more in between. I'm going to talk about them. I'm going to talk about, in particular, I'm going to talk about one of them. I'm not going to talk about all of them. I'm going to talk about one of them. That's what I'm going to do next. You follow me? What's the other isolation level that's not so weak as interleaving any action as you wish, as he has suggested, but at the same time, is not as restricted as the serializable isolation level I just talked about. You follow this? Let's talk about that. In particular, before I proceed, it will be interesting to figure out what isolation level we are running in the MySQL database or where are you? You want to figure out? Yeah, let's do that. Okay? So you can figure out the isolation level of your database engine. Typically, there's a variable like this, something called isolation. Okay? Let's look at what isolation level typical database engine are running at. Oops.
We can't see.
Sorry. Like as if I were running isolation. Seriously. Like, seriously, that's exactly running isolation. I don't care what you say, as if I'm running isolation. Perfect. Okay, now, let's switch. Okay? Repeatable rate. Repeatable rate. And what does that isolation mean? And that's exactly what I'm going to show you next. You follow this? Okay, what is the repeatable rate isolation level? Back to the slides. Before I talk about repeatable rate isolation level, let me introduce this concept called dirty rates. A dirty data item is any write done by an uncommitted transaction. Any write done by an uncommitted transaction. For example, the couple examples I demonstrated so far in my lecture, if I insert into student table, and I haven't committed yet, then that newly inserted student record is a dirty item, because I haven't committed yet. As another example, I multiply 1.1 to all student GPA values. For some reason, I decided to give 10% bonus, just like bank give out 10% interest. Never happened. Both of this never happened. Bank will not give you 10% interest. You will not get 10% bonus on your GPA. Too bad. Come back to the reality, guys. I haven't committed yet. So 10% bonus, then go back. Okay. So this, if I do that, all student records will be dirty items because they have uncommitted updates pertaining to be committed or rollback. So that's the definition of dirty item. Now, once you understand dirty item, dirty rates become simple, right? Dirty rates is another transaction try to rate a dirty item. That rate becomes a dirty rate. Let me give you an example. Okay, let's say enrollment. I just inform my staff. Let's say I'm the admission officer in the University of Utah. I inform my admission office that, oh, I just admitted 1,000 students, so the enrollment number is updated by 1,000. And this is concurrent with another person trying to execute a statement saying, I want to get the average, for example, enrollment from Pac-12 schools. You follow this? Now, if you try to rate, by doing this, you have to rate the enrollment value from each university from the Pac-12 colleges. When it comes to the University of Utah, and suppose that's right after you have updated enrollment number by 1,000, that rate of the enrollment value will be a dirty rate because that first statement or first transaction hasn't committed yet, assuming it hasn't committed yet. And if you allow that rate to happen, then that becomes a dirty rate. You follow me? Do all of you follow this? And dirty rates cause a lot of problems. Why? Because since that rights have not been committed yet, and if you allow a dirty rate to happen, the problem is that first transaction may come back and decide to go back. besides rollback. And when that happens, the second transaction is forced to roll back as well, because now you're relying on inaccurate values. So the second transaction will be forced to roll back as well, even though the second transaction doesn't want to roll back, but you will be forced to roll back because of that dirty rate. Okay? And imagine that's concurrent with yet another statement that depends on that, and this will have this domino effect, as you can imagine. Right? Like, domino, right? Domino cards. You push down one, then a whole sequence, a whole chain of them will go down. So if you allow dirty rates to happen, that rollback, this is what we call cascading aborts. The rollback or abort of one transaction will lead to a sequence of rollbacks and aborts of other transactions who depend on one another. Okay? This is the problem with dirty rate. Because of this, to disallow things like this to happen, people define this isolation level called repeatable rate. Repeatable rate has only two requirements. One, a transaction may not perform any dirty rate, no dirty rate. Secondly, an item read multiple times cannot change value. If I read the value of enrollment for the first time, it's solvent. If I'm still in the same transaction later, I read that enrollment value again, it should be solvent, unless I myself have made some changes. By the way, if you're reading a write performed by the same transaction, that's not considered a dirty rate. Dirty rate is you read an uncommitted item written by another transaction. Reading your own update is always okay, of course. Otherwise, you cannot proceed. You don't allow that, nothing can happen. So repeatable rate has only these two requirements. And you may wonder, okay, fine, let me go with these two requirements and why this is a relaxation of serializability. Why this is considered to be a relaxed version of serializability. To show that, all I need to show is the following, which is I can have some schedule, interleaving of action from different transactions, that will be rejected by the serializable isolation level, but somehow allowed by repeatable rate. If that's the case, indeed, repeatable rate is a relaxed isolation level than serializable, right? That's serializable isolation. All we need to do is to show that. To do that, we come back to the same example I used earlier in my lecture. Again, this particular schedule, where I'm interleaving action from different transactions, in this case only two transactions. Earlier, I have already argued that this is not allowed in serializable isolation level. Why? Because it's not equivalent to T1 and T2. It's also not equivalent to T2 and T1. So it's rejected. If you run your database engine in serializable isolation level, this will be rejected. You follow me? Now let's check the same schedule and see whether this is allowed in repeatable rate. Can someone tell me whether this is allowed in repeatable rate or not? Looking at those two conditions on top. Is this allowed in repeatable rate? Let's check one by one. First of all, is there any dirty rate? How many say there is dirty rate? How many say no dirty rate? So you mentioned there no, yes or no? No, okay. In this case, there are no dirty rates. Why? The only write, the only update we have is caused by this statement, right? And indeed, it's been read by the selection statement down below. However, the point is it has committed before you execute that second selection statement, which means, yes, the transaction 1 does read this value, does this with this new update, but it's a committed write. It's no longer an uncommitted write. If I were to move this commit to here, that becomes a dirty read. You follow me? If I remove commit from here and commit only after the second selection statement, that second selection statement will perform a dirty read. But because I committed before that, it's no longer a dirty read. Okay, so condition 1, check. Condition 2, item write multiple values, multiple times cannot change value. Do we have an item write multiple times, more than once, that has changed value? This is actually a little bit tricky. Yes or no? I'm going to say yes. I have item write multiple times change value. Which one has changed value?
Age, right?
Huh?
Age.
Say again?
Age has changed.
Age has changed. Which age?
The entry user has changed, right?
Say again?
We inserted something into
You inserted, okay, that's the item. This is item. This is a single item, right? A user record is item here. But it's only been read once. The first time it was read is here, and value didn't change. Item read multiple times cannot change value. Which item being read multiple times? First of all, can you tell me that? What item have been read more than once? Someone who are already there in the database, age between 10 and 30. Excellent. Have those guys changed values? No, none of those have changed values. Okay? So no item being read multiple times have changed values. Henceforth, this satisfies the repeatable read requirement. Go ahead. And if that existing entry being read twice. So this particular schedule will be allowed in repeatable read isolation level. However, as I argued for the third time today, it will be rejected under the serializable isolation level. This shows you that serializable isolation level is indeed the strictest, the most strict requirement in terms of allowing action to be interleaved from different transactions. Repeatable read relax that. By relaxing it, what does that mean? That means your database can perform at a higher throughput, can serve more users at the same time. That's why when you go to delta.com or expedia.com, when you book your flight, sometimes, it doesn't happen all the time. I don't know whether it happened to you guys before or not. It happened to me all the time. God, I book so many flights, I fly all the time. That's why I watch special applications, it's important. Now, it happened to me when when I go through the booking process on Expedia or Delta.com. I made my reservation. I take some time to consider whether I want to finalize my purchase, right? Sometimes you think for just a second or a minute, you click that finalization or confirmation button. The system, most times it says congratulations, okay, it's done. Sometimes it comes back and says sorry, it's no longer available. Book again. You see what I'm saying? The reason is they're not using serializable isolation level because they want to achieve better performance. They're using something weaker than serializable isolation. Typically repeatable read or something called read committed. And there's another thing called snapshot isolation. These are all different variations of isolation level that allow weaker guarantees, but at the same time, increase the degree of interleaving execution of transactions. Next time when you book something on Delta or Expedia, this happens, don't be panicked. I'll see you on Monday.